What is up, everyone, and welcome to another episode of The Rockstar Scientist. My name is Dr. Scott Askinosi, the Rockstar Scientist, and today we're going to be talking about Unit 6. So, a little bit of a mixed bag today. You're going to get some information about Earth layers, you're going to get a little bit about convection and what that means in the Earth, and then lastly, we'll go into plate tectonics. So, hopefully we'll be able to get through it all in the next 45-50 minutes. But yeah. Let's get started. Okay, so if you look here, I've got an image of the layers of the Earth. It's kind of like a cross-section, a little candy corn guy, if you will. And what we have here is Earth has three main layers. It has the top layer that we're most familiar with called the crust. It has the central layer called the mantle. And then it has the inner layers that we call the core. Now the crust is pretty thin relative to the rest of the Earth, because it is, it's like the crust on a piece of bread. The crust is usually the thinnest part because it's just the outside, the hard outside, and then the rest of the Earth is the, not always soft, but we'll say softer inside. Okay, so the crust here is what we're most familiar with. This is going to be everything on the outside that we interact with every day. Below the crust is the mantle. And the mantle layer is actually divided into two pieces. There is the lithosphere, and then what we call the asthenosphere. The lithosphere is here on the outermost part of the mantle. And the lithosphere is a lot like the crust. So, in fact, a lot of geologists will actually combine the two together and talk about them as basically kind of the same layer, because they're so similar. Whereas if we go a little bit deeper, we hit the asthenosphere. Now, even though the lithosphere, and the asthenosphere are part of the same layer of the Earth, they're quite different. First off, the lithosphere is a lot more like the crust, so it makes it really hard. Whereas the asthenosphere is not. The asthenosphere is made of magma, also known as hot lava, which I'm sure you all are familiar with. And as you know, lava isn't hard. It can flow. It doesn't flow like water, so it's not completely liquid, but it's not completely solid either. So we say that the asthenosphere is plastic. And this is important because this is a really great test question when they ask about what is the most plastic, or what do we consider the plastic part of the Earth's layers. And when we say plastic, we don't mean plastic like a water bottle. We mean plastic as in it's malleable. And to be malleable is to be able to be formed. So it's not quite solid, but it's not quite liquid either. So this layer is plastic because it has the consistency of like mud or like clay or silly putty, something that you don't want to do this, but you could form with your hands if you wouldn't melt because it's so hot. So the asthenosphere is plastic, and we like to think of that as lava or magma. Magma. So liquid molten rock, semi-liquid molten rock. Okay, the core is a little bizarre because it is a little counterintuitive the way that its consistency works when we talk about the outer versus the inner core. So the core is divided into two pieces: the outer core and the inner core. Now the outer core is liquid because the closer you get to the center of the Earth, the hotter it gets. So the outer core is going to be liquid. Now, if the closer you get to the center, the hotter it gets, you would expect the inner core would be liquid as well. The inner core is actually solid. So what's the deal? If it's so hot it liquefies everything, why is the inner core solid? It's because of gravity. So gravity originates from the center of the Earth. And gravity at the center of the Earth is so strong that it prevents that portion from being liquefied. So even though it's technically hot enough to where the inner core could be liquid, gravity keeps it so squished together that it's actually solid. So the outer core, super hot, liquid. The inner core is even hotter, but because gravity is so strong, it's actually solid. And another important thing to note, the core is made primarily of iron and nickel, whereas the crust is made mainly of what we call silica or silicates. So nickel and iron, you probably know what those are. They're metals. So the outer core is liquid metal and the inner core is mostly solid metal. Silicates, though, you may not be as familiar with. So when you think of silica, think like sand. Sand has a lot of silica in it. So silica is going to be like dirt as far as you're concerned. There's a lot of dirt on Earth, so you know the crust is made mostly of silica. Okay, so those are the Earth's layers. Now, I'm going to draw you a very awful drawing of the Earth, and we're going to talk a little bit more about these layers and why they're important for the rest of the units moving on, or the rest of this unit moving forward. Okay, so we've got the crust there. I'm just going to draw this here. We'll call this the mantle. So we're just going to pretend for now that the lithosphere and the crust are one and the same because they're so similar. So there's the mantle, and then I'm going to go and draw the inner core and the outer core a little bit different. So we'll choose this color here. This is going to be the border of the outer core. And then to keep with the color scheme we have over there, the yellow, this is going to be the inner core. Okay, so here we have the crust and the lithosphere together. Then we have the asthenosphere here in red. So this is the asthenosphere. And then we've got the outer core and then the inner core. Okay, so before we talk any more about these layers, I want to introduce a concept to you called convection. Convection, because it's actually really important for a lot of Earth processes. So a good example of convection would be something that you are probably all familiar with. If you can tell what my awful drawings are, that is. Okay, so this is supposed to be a pot of water. And let's say that you've got that pot of water on the stovetop. So you've got it sitting on your gas or electric range. You probably recognize convection from convection ovens, where rather than just baking from the bottom, it uses a circulating air current to make sure that you cook the food from all sides to get a nice even bake. Convection actually is a natural phenomenon that describes the way that heat moves. So here, we're going to show, or I'm going to show you exactly what convection means when we're talking about convection currents, because convection currents are really important in the world. And you'll see what I mean here in a second. So when we have our pot of water sitting on the stovetop, we're heating it from the bottom. So it's going to be heating all the water on the bottom of that pan up more than it is the stuff on top. So which means the water on the bottom of the pan is going to become hotter relative to what's on top. And what do you guys know about heat? Where does heat like to go? Heat rises. So these warm water molecules are going to rise to the top of the pot here. And as they do, they begin to interact with the cooler water. And when they hit the air here, the air is a lot cooler. So what they do is then they cool off and then they cycle back down, creating this, what we call a current. So the water moves up as it gets hot, it interacts with the cold water on top, and then it falls back down to create this cycle, a convection current. This is why when you boil water, you see the bubbles form actually at the bottom of the pan and then rise up, because that is hotter relative to the rest. Also, it would be a little difficult to see, but if you took some like food coloring and dropped it in to a hot pot of water, you may see that these cycles. You'd be able to see that the water isn't stationary, that it's actually moving. And convection currents not only occur in water, but they actually occur in the Earth as well. So let's look here at our semi and mostly liquid portions of the planet. So heat comes from the inner core, right? That's where the heat is generated. Also where gravity comes from, so the core is really important. Now the outer core is liquid, and there's a lot of heat coming from the inner core. So what that's going to do is it's going to cause that liquid portion that's closest to the inner core to heat up. And as it does, it's going to rise, because heat actually expands. So that's why we say heat rises, because it's always trying to escape. It's always trying to go outward. And for us, standing on Earth, outward is up. So this warm current is going to moving outward or upward, depending on how you want to look at it. It's going to interact with the cooler part, which is going to be the asthenosphere, the magma portion, and it's going to fall back down, creating a convection current. So the liquid portion of the outer core is actually flowing, because all these currents create essentially a flow. And what this flow does is it causes the inner core here, this solid portion within the liquid portion, to spin. So the inner core is actually spinning in here. Now remember, the inner core is made of iron and nickel, which generally exist with a charge. So let me ask you this. Thinking back to Module 2, what do you get when you have charged particles that are in motion and or, in this case, are spinning? You generate a certain type of field. Hopefully you guessed it. It's what we call a magnetic field. And this is why the Earth has magnetic north and magnetic south, because the inner core is spinning within the liquid portion of the outer core, generating an electric field. Magnetic field. And this magnetic field is really important because it gives us north and south, but it also does something else. So as you guys know, the sun, we talked about this in Module 4, Part 2, or at least in the Rockstar Scientist videos. It's in a different module within the unit. I can't remember which one off the top of my head. But the sun is undergoing thermonuclear fusion. So when it takes those two hydrogen atoms and smashes them together and make a helium, it releases a lot of energy. And energy, as you know from Unit 3, is radiation. So the sun is releasing heat radiation, it's releasing light radiation, it's also releasing gamma and X-ray radiation, and ionizing radiation. So all this radiation is raining down on us from the sun. Ionizing radiation actually gets deflected or caught in the the magnetic field from Earth, which is really fortunate for us, because if we were exposed to this ionizing radiation, it would be very detrimental to our tissue. So this magnetic field actually prevents the ionizing radiation from the sun from reaching us. So it acts as kind of like a shield against these really harmful rays of radiation coming from the sun. In that region of our atmosphere that these ions or this ionizing radiation from the sun gets deflected is called the ionosphere, which you will remember if you have studied what's in Unit 6 about the different layers of the atmosphere. Okay, so that's the first example of convection on Earth. The next one happens here in the asthenosphere. So the asthenosphere isn't fully liquid, but it's still partially liquid. So it is subject to convection currents as well. Now, convection current occurs as the heat from the core is moving outward into the asthenosphere. And what it does is it causes this part of the asthenosphere to heat up just like before. And then it reaches the crust, which is cool, and it cools off, and it comes back down, creating, again, another convection current. So this magma underneath the surface of the Earth in the asthenosphere is actually flowing because of these convection currents. So it's like this river of magma that's constantly flowing underneath the Earth. So why do we care about that? What does that do? Well, the plates of Earth, so when we talk about plate tectonics, the tectonic plates, which are made up of the crust and the lithosphere, these huge land masses and the land that exists underneath the ocean, these plates are all floating on the asthenosphere. They're all floating on that river of magma. So as this magma flows, it causes these plates to crash into each other, or to slide away from each other, or in some instances to slide past one another. So the convection currents within the asthenosphere, within the liquid portion, this flowing of magma is what causes plate tectonics. This is why the plates are always moving around, because they're floating on this river of magma. If you think about it, it's all like an ice sheet floating on the water on the ocean in the Arctic Ocean. Sometimes the ice can crash into each other, sometimes they can move away from each other, and sometimes they can just slide past each other. Same basic principle on Earth that you would expect to see like an iceberg floating on water. Okay, so that's a second example of convection. There's actually a third one. So, Earth has different regions that experience different temperatures year-round. So, in the northern hemisphere, we have a summer, a spring, a fall, and a winter. And in the southern hemisphere, their seasons are actually opposite ours. So when we're experiencing winter, they're experiencing summer because of the way that the planet is tilted. But there's this region in the center that we call the equator, and the Tropic of Cancer and the Tropic of Capricorn, where they don't really have seasons. It's beautiful and sunny and perfect all year round. And that's because they are not affected as much by the tilt of the Earth. So they receive direct rays of sunlight all year round, whereas depending on the season, we'll either receive more direct or more indirect. But it's not going to be as direct as that center portion, generally. So the tropics, nice and warm year round. So this region of the globe stays nice and warm, which again is the perfect conditions for a convection current. So check this out. We have the sun that's shining hard on in the tropics all year. What that does is it causes the regions here to warm up relative to the regions around them. So that's going to cause warm air to rise. And as it does, it interacts with the cooler parts of the atmosphere, which causes it to fall. And as it falls towards the poles, because poles are the coldest regions. And as it falls there, it actually pushes, just like a typical convection current, cold air back from the poles. This convection current is called helicell. So if you look in your study guide in Unit 6, you should see that there's an area that asks about helicells and what they are and what causes them. And this is basically what it is. So helicells are what drive worldwide weather patterns. So if we have a hotter summer, which is generally followed by a cooler winter. And part of the reason for that is because, I mean, look at it. You have all this hot air. If it's a hot summer being pushed towards the poles, naturally it's going to push more cold air back towards the tropics. This also helps partially explain why we begin to have more extreme weather during warm summers, because these convection currents contribute pretty heavily to things like hurricanes. So if we have more hot air that's moving, we're going to generate more large storms. So that's why, another reason why, rather, things like global warming and increased temperatures are really a big problem, because more storms means, or more warm air movement means larger storms, which means, you know, more devastation to people that live in areas that are subject to hurricanes. Okay, since we're talking about that, what causes a hurricane? Well, this is actually kind of a neat concept. I mean, subjectively neat. You may not think so. But so the Earth is tilted, and it rotates on its axis. So the Earth actually rotates this direction. So it goes this way. And that's why the sun appears to rise in the east and then set in the west. Okay, so we have these wind patterns that are moving like this. And this is what, the movement of the Earth is what causes hurricanes to initiate that spiral pattern. And this is called the Coriolis effect. Coriolis? I don't know. You can get the spelling from your study guide. I'm not an English teacher, just a scientist. So the Coriolis effect is caused by the rotation of the planet. And it's kind of a difficult concept to grasp, but let me draw you a little very poorly drawn picture to help illustrate this. So let's say that you're hanging out here on the equator, and you're playing catch with your buddy that's up here in the northern hemisphere. So you're going to throw a ball right to him, or at least that's what you try to do. But it takes time for the ball to get there. And as the ball is traveling towards him, the Earth is rotating. So by the time the ball actually reaches him, he's not standing there anymore. He's actually over here. So it looks to him as if you threw the ball way to the left of him. Or wait, let me think. Yeah, right? Yeah. So this movement of Earth is what causes the Coriolis effect. This is what causes those wind patterns to begin to spiral. Because air isn't totally tethered to the planet. It is somewhat influenced by gravity, but it's not like us. It's not stuck to the planet like we are. So this movement of the Earth is going to cause those spirals to occur as the wind travels from the equator towards the poles. And again, why hurricanes have that spiral pattern. In fact, this is kind of a little fun fact, if you will. In North America, in the Northern Hemisphere, because of the Coriolis effect, hurricanes and tornadoes actually spin counterclockwise. Whereas in the Southern Hemisphere, they spin clockwise. Again, it's all because of the rotation of the planet. So if you flush your toilet, you may notice that it spins counterclockwise. If you call a buddy in Australia, have them flush their toilet, it actually flushes the other direction. Crazy, right? Okay. So that about does it for convection. So now that we talked about convection, let's go back to what we talked about a minute ago, plate tectonics. So I told you a second ago that these plates are floating on the stenosphere, this river of magma, and that's what causes them to either crash into each other or separate. So now let's talk a little bit about what the results are from each one of those plate interactions. So here we're going to be talking about plate tectonics. Plate tectonics is essentially describing when two plates come together. When two plates come together, it's also called a plate boundary. So if you see this, it's basically the same thing. And there are three types of interactions that plates can have. The first is convergent. So plates can converge. To converge is to come together. So they can crash into each other. The second is divergent, where plates are actually moving apart from each other. They are diverging. And the third is transform. And this is where they're neither coming together or moving away. They're actually, do this on the screen, they're actually sliding past each other. See that? Okay. So those are the three types of plate boundaries we have on Earth. So let's talk a little bit about examples of each. And we'll start with convergent. And there are three examples of this here on Earth. There are three types. Maybe types is better. There are three types of convergent boundaries. And that may seem like a lot, but I promise once we start talking about them, it'll make sense. So before we get there, though, there are two types of plates. So plates themselves can either be land or they can be underwater. So you can either be a land plate, which we call continental, or you can be underwater, which we call oceanic. So those are the two types of plates. You can either be continental or oceanic. But we're still talking about there are three types of convergent boundaries. So based on what I just told you, you can probably guess. The three types of convergent boundaries are you either have two continental plates coming together, an oceanic and a continental plate coming together, or two oceanic plates coming together. There are no other options. So let's talk about each one of those. Let's start with oceanic, because oceanic is kind of the most fun. So oceanic plates, or no, actually, you know what? I got a better idea. Let's start with continental and oceanic so that I can really show you the difference between the two. So there are instances where a plate that's underwater, it's called an oceanic plate, will actually collide with a continental plate. So before we talk about this, it's important to note the relative size of these two plates. So the continental plate looks a lot bigger than the oceanic plate. I drew them that way on purpose. That's because they are actually a lot larger. But the oceanic plate is actually a lot more dense. So this is oceanic. This is continental. And the oceanic plate is very dense. And there's a reason for this. Oceanic plates exist underneath the ocean. And anybody who's ever tried to change the Culligan bottle on their water cooler knows water is really stinking heavy. So imagine you are a plate underwater, and for the last 6 million years or whatever, more than that, probably 13 million years, you've been covered. Actually, I think it's even longer than that. Anyway, it doesn't matter. You don't even know that. I don't even know that. For the last however many years, you've been sitting underneath millions and millions and millions and millions and millions and millions of pounds of water. And that water is just crushing you every single day. So what we get is those plates have been crunched down. So they're smaller, but they're going to be a lot heavier. They're going to be a lot more dense. Whereas the continental plates have not been under that pressure. So they are a lot more, like, I think the videos that you have in your class say fluffy. And we know that rocks aren't fluffy, but if you look at, like sandstone compared to something like steel, A, steel is a lot heavier than sandstone, and B, it's a lot harder to break. It's a lot more dense. It's a lot stronger. Same basic principle here. Oceanic plates are super compact, so they're real tough and real dense. And this is important because this is going to influence how they interact when they come together. Okay, so let's look and see what happens. These two plates are floating on that liquid, on the lava, on that river of magma, and they're going to crash into each other. When they do, the oceanic plate is actually going to slide underneath the continental plate. And this is an event we call subduction. To subduct is to move underneath. So the oceanic plate, because it's really heavy, is going to go underneath the continental plate. But there is a lot of lava down here, remember? Because these are all floating on this river of magma. And this magma has to go somewhere. If you're going to push something down into it, it's going to have to squirt out somewhere else. It's a lot like, if you remember the old Play-Doh barbershop set, where you would take the guy and you'd fill his head with Play-Doh and you'd smash him down on the barber's chair and they would squirt out of his head like spaghetti. Same basic principle. You're pushing this oceanic plate down into the magma and it's going to have to squirt out somewhere. So what it's going to do is it's going to work its way up through this continental plate until finally it erupts. Now when it erupts, it's going to start to squirt out, and it's going to dry, and it's going to make a peak, and it's going to squirt out some more, and dry and make a peak, and so on and so on and so on, until you have this set of mountains that we call a volcanic mountain range. So again, one more time. Oceanic plates going under, it's Play-Dohing, Play-Doh barbershopping, squirting all that lava out through the continental plates, and it's going to make volcanoes, which are going to eventually make a volcanic mountain range. So in Argentina, there is an example of this where an oceanic plate comes together with a continental plate to make the Andes Mountains. There's one other thing that's formed during this process. If you look right here, there's a little area, a little divot here of negative space that we call a trench. So it's just like a big gap. And this big gap is something that you can also see off the coast. It's just like this area where the ocean gets super deep. And for the longest time, they're like, what's going on here? And they're like, oh, it's because we've got plates there. Okay, so when you have a continental plate and an oceanic plate coming together, you're going to get a volcanic mountain range on land and then a trench in the water. All right. So now let's see what happens when we have an oceanic plate coming together. So these are both really dense. But, as you can probably guess, the same thing happens. Whenever you have an oceanic plate involved, one of them is going to subduct. One of them is going to slide under the other one because they're so heavy. And when they do, same thing as before, all that lava's got to go somewhere. So it's going to work its way up through this oceanic plate, and it's going to erupt, and it's going to harden, and it's going to erupt, and it's going to harden, and then it's going to erupt, and it's going to harden until we get this mountain that protrudes the surface of the ocean, which is called an island. So this is where you get volcanic island chains, much like those in Hawaii or Thailand. And again, just like before, you have this area of negative space we call a trench. Pretty simple, right? Anytime there's an oceanic plate involved in convergence, you're going to get some type of volcano because it's going to subduct and it's going to squirt that magma out. Okay, and that's really it. It's very similar to the last one, so we won't spend much time on it. Okay, the last one, the last example of convergence is when we have two continental plates. Okay, so as you can see, neither one of these are that dense. They're both fluffy. They're not compact. So when they come together, they're not going to subduct. What they're going to do is they're going to crash into each other, and it's going to be like crumpling a tin can. They're going to splinter. They're not going to slide underneath each other. They're just going to go like... In that case, what you're going to get is just a good old-fashioned mountain range. So this would be like, if I'm not mistaken, the Continental Divide. Because as far as I know, there are some ancient dead volcanoes in like Washington, or Mount St. Helens because it's not technically dead, and Montana, a few active things in Yellowstone. But as far as I know, the Continental Divide was not made by volcanic activity. It was made by continental plate boundary. And I mean, not super exciting. That's really all you get. Get a mountain range. Okay, so that's it for convergence. So now let's talk about divergence. Now, oh, come on. So divergent, man, it's a lot harder to spell when you're writing in front of a camera than you think it's going to be. So divergent, there are only two types. And those are continental and oceanic. Let's do oceanic first. Oceanic's more interesting. Okay, so there are areas where we have two oceanic plates that move away from each other. Now, as you know, as we talked about, oceanic plates are super dense, and because of that, they're really heavy. So they actually are technically a little bit closer to the magma because they kind of squish down on it. So when we have oceanic plates move away from each other, we're going to get leakage from the asthenosphere. So lava is actually going to work its way up from the asthenosphere. As these two move apart, water is going to move up or come out, and as it does, it's going to solidify, and it's going to make these little mountain peaks. So it's not going to erupt necessarily. I mean, not necessarily. Probably does a little bit, but not the way that you would expect when you've got a plate that's actually forcing it out. But as it comes out, it's still under a lot of pressure, so it's going to work its way up. And when it does, it hardens to create these mountain ranges deep, deep, deep underwater that we call an oceanic ridge. So there's one of these in the middle of the Atlantic Ocean where you can see with, satellite images, that deep, deep, deep underwater, there are these huge mountain ridges. Or maybe you can't see them with satellites, I don't remember. Because I think that some of these are so deep, light doesn't even penetrate that much. But anyway, they're there. So anytime you have two oceanic plates moving away from each other, you get a mountain range deep underwater that we call an oceanic ridge. Which leads us to what happens when we have two continental plates that are moving away from each other. So unlike the oceanic, we don't get that bubbling up as much of magma as we did before. So you're not going to end up with this mountain range in here. Rather, what you're going to end up with is something else. We'll talk about that in a second. So if these two plates are moving away from each other, naturally you're going to have a big hole, which is what you see. This like huge gap. It's like flat, 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 no mountains or anything, all of a sudden, big hole. And this is called a rift valley. We don't have any of these here in the United States, but I believe there's one in Africa and one somewhere in the Middle East, where yeah, it's just like flat and all of a sudden, big hole. So the Grand Canyon is not one, but you can imagine if you've ever seen pictures or seen the Grand Canyon, what it would be like. You're just driving along, all of a sudden, huge gaping hole. So we don't get mountain ranges within this rift valley like we do in the ocean, but sometimes this magma will kind of seep up and create little rock formations. They're not going to be mountains, they're just going to be like these big ugly rocks that do not look like they belong there because they are igneous material. They are magma that is solidified to make an igneous rock that looks really out of place. And we call this new crust material because it is newly formed from magma. Okay, so that's it for divergent. Pretty simple, right? Okay, the last one we're going to talk about are these transform boundaries. And this is where we have two plates that actually slide past each other. Now, the transform plates that you're probably all used to are those in California. So what do you get when these slide past each other? Well, one of the things you get is you get a bunch of earthquakes. Because as these slide past each other, they can release a lot of pressure that's built up in that rock, and it causes the earth to shake, also known as an earthquake. Another thing you get is what we call a fault line. So it's the line essentially at which these two plates are sliding past each other. And an interesting thing to note about transform boundaries is that if you have some type of land formation that crosses this fault line, you're going to see that eventually it's going to become disjointed. In fact, scientists have determined that in like 1,000 years or something like that, LA and San Francisco are going to be neighbors because they're on opposite sides of the fault line and they're slowly moving towards each other, which is kind of bizarre if you think about it. Okay, so I think that's really it for plate tectonics, convection, and Earth's layers. At least as far as we need to talk about for today. So as per usual, thanks for hanging out with me, and thanks for listening, and thanks for watching. If you have any questions whatsoever, feel free to contact me anytime. My email and my extension are all there. Or feel free to reach out to the Natural Sciences inbox. That can be accessed through your course of study. It's right there on the right-hand side, right below the picture of your course instructor. Or reach out to us on Chatter, or you can do live chat. However, if you have any questions at all, feel free to reach out at any time to myself or any of the other course instructors. We're here to help. But thanks again. I really appreciate your attention, and I'll see you next time.